The art of crafting algorithms, a deep dive into algorithm development in the ever-evolving world of technology. Algorithm development stands as a cornerstone of innovation. Whether you're designing an AI model that can predict stock market trends or optimizing a logistics network to reduce delivery times, algorithms are at the heart of every digital solution. This guide explores the intricate process of developing efficient and effective algorithms tailored to solve complex problems across various domains. From conceptualization to implementation, we'll unravel the key principles that define successful algorithm design. Understanding the foundations of algorithm development. An algorithm is essentially a step-by-step procedure designed to solve a particular problem or perform a specific task. At its core, an algorithm must be unambiguous, finite in steps, and capable of producing correct outputs given valid inputs. Before diving into coding, developers often sketch out their ideas using pseudocode or flowcharts. This preliminary phase helps identify potential issues early on and ensures that the logic aligns with the intended outcome. Efficiency remains paramount in algorithm development. While correctness is crucial, an inefficient algorithm may lead to performance bottlenecks even when the logic appears sound. Measuring efficiency typically involves analyzing time complexity, how long an algorithm takes, and space complexity, memory usage. These metrics help determine whether an algorithm will scale well under different conditions. Consider two sorting algorithms. Bubble sort has a worst-case time complexity of O(n) superscript 2, while merge sort maintains O(n) log n, regardless of input size. Choosing between them depends heavily on expected data sizes and constraints. Correctness proofs play another vital role. Formal verification techniques ensure that an algorithm behaves exactly as intended through mathematical induction or other rigorous methods. The iterative process of designing effective algorithms, creating high-quality algorithms, rarely happens on the first attempt. It's an iterative process involving continuous refinement based on feedback from testing phases. Developers often start with brute force approaches before gradually optimizing towards more sophisticated solutions. For instance, finding the shortest path might initially involve checking all possible routes, then refining it via Dijkstra's algorithm once patterns emerge. Coding challenges such as those found on platforms like LeetCode provide excellent practice ground for honing these skills. They allow practitioners to experiment safely without real-world consequences. Each iteration provides new insights. Sometimes minor adjustments yield significant improvements. Other times complete overhauls become necessary depending upon changing requirements or newly discovered limitations. Evaluating performance through benchmarking. Benchmarking plays a critical role in assessing how well an algorithm performs relative to others solving similar tasks. Tools like JMH for Java or PyTest for Python enable precise measurements across varied datasets. Datasets used during benchmarking should reflect typical scenarios rather than ideal ones. Realistic test cases include edge values, outliers, and varying input sizes to stress test the limits effectively. Consistent benchmarking practices reveal not only average case behavior but also worst-case scenarios, which are essential knowledge when deploying systems handling unpredictable workloads. For example, comparing quicksort against heapsort under different distributions shows variance in performance that informs better decision-making regarding suitability for targeted applications. Best practices for collaborative algorithm development. In today's collaborative environments, working together efficiently becomes indispensable, especially when tackling complicated projects requiring multidisciplinary expertise. Version control systems like Git facilitate seamless collaboration by tracking changes made by each contributor, ensuring transparency and accountability within teams. Code reviews serve dual purposes, improving code quality and promoting shared understanding among team members. Constructive criticism fosters growth while identifying areas needing clarification. Establishing clear communication channels enhances productivity significantly. Regular meetings, documentation updates, and utilizing project management tools maintain alignment throughout development cycles. Fostering innovation through peer review sessions. Peer review sessions encourage open discussions where alternative viewpoints challenge existing assumptions, leading potentially toward breakthrough innovations. Diverse perspectives contribute uniquely towards resolving technical hurdles more creatively. By embracing differing opinions constructively, teams increase chances discovering novel methodologies applicable beyond immediate scope. Such interactions cultivate an environment conducive to experimentation, reducing fear associated with failure, thereby encouraging risk-taking behaviors beneficial long-term progress. Encouraging questions during peer reviews ensures everyone fully understands implications behind proposed implementations, reinforcing collective ownership over final products. Leveraging data structures for optimal solutions. Selecting appropriate data structures forms half the battle in creating efficient algorithms. Different operations have distinct impacts based on underlying implementations chosen. Arrays offer fast access times at expense of insertion/deletion costs, whereas linked lists excel dynamically expanding collections, though traversal requires extra effort compared to direct indexing. Trees structure hierarchical information, enabling faster lookups than linear arrays, particularly useful implementing search functionalities, leveraging binary trees, etc. Graph theory introduces powerful abstraction mechanisms modeling relationships between entities, allowing application-specific customizations suited diverse needs ranging social networks, traffic routing, etc. Choosing between hash tables versus trees for lookup operations. Hash tables provide near constant lookup speeds, assuming uniform distribution, eliminating need binary searches, inherent tree traversals, and less collision resolution strategies employed. Trees inherently support ordered data, maintaining sorted order, facilitating range queries. Impossible hash tables since they store arbitrary keys lacking natural ordering properties. When dealing with frequent insertions deletions alongside occasional range queries, balanced BSTs prove superior alternatives, offering logarithmic operation complexities comparable hashing yet additional functionality. Implementation choice ultimately hinges upon frequency analysis, determining dominant operations, influencing optimal selection between competing structures. Navigating common pitfalls during implementation phases. Misinterpreting problem statements frequently leads developers astray, resulting wasted efforts addressing wrong objectives, entirely unrelated original intent. Precise specification parsing prevents costly rework later stages. Clarifying ambiguities upfront saves considerable debugging hours down road otherwise spent correcting misaligned expectations. Overlooking boundary condition tests constitutes another common oversight, undermining robustness. Deployed solutions failing gracefully unexpected situations. Rigorous unit testing covering extreme value cases guarantees reliability, enhancing trustworthiness. Implemented functions irrespective external influences affecting execution contexts. Debugging techniques specific to algorithmic problems. Print statements remain basic debugging tool, revealing internal states, helping trace logical errors originating obscure locations difficult isolate otherwise. Interactive debuggers empower step-through examination, observing variable transformations frame by frame, pinpointing exact moment divergence occurs from anticipated results. Using assertions validates intermediate computations, flagging discrepancies immediately, halting further processing until root cause identified resolved satisfactorily. Profiling utilities detect performance anomalies, highlighting hotspots warranting optimization attention, ensuring resource utilization stays within acceptable thresholds, defined system constraints. Staying updated with emerging trends in the field. Technology evolves rapidly, necessitating ongoing education, keeping abreast latest advancements shaping future directions. Industry landscapes. Participating conferences, workshops exposes professionals, cutting-edge research developments, fostering connections, colleagues pursuing similar interests, enhancing visibility, networking opportunities. Following academic publications, journals provides authoritative sources, theoretical foundations guiding practical applications, translating abstract concepts, tangible outcomes benefiting broader communities. Engagement, online forums, discussion groups facilitates exchange ideas, experiences, accelerating learning curves, cultivating supportive ecosystems, nurturing continuous improvement trajectories, personal, professional growth alike. Conclusion: algorithm development is both art science demanding precision, creativity navigating multifaceted challenges, successfully delivering impactful solutions meeting evolving demands, modern computing paradigms. By mastering fundamentals, employing best practices, continuously refining techniques through collaboration, innovation stays within reach, empowering individuals, organizations, transform visions, realities, driving technological advancement forward relentlessly.